Hello, this is IA, and today's video is about another unit of IAPC8, the computer I made on Minecraft. And this is gonna be on the ALU, which is the Arithmetic and Logical unit, the center of operations in the computer, basically. So this unit is pretty simple in itself. What is complex about it is the computations you're gonna make, like if you decide to have a multiplication, a division, or any kind of complex stuff, this goes with the operand in itself, but not the unit. So basically the first thing you need to know is this unit is mainly working with two operands. We need two input values on 8-bit because our computer is in 8-bit, but the design of the computer is made so that we can communicate between units with only one 8-bit value. There's no complex stuff like pipelining or tons of registers. A real simple design. The principle is that I input a value as first operand, and then I have registers. I have actually two registers for the operand A and the operand B, like the two operands. And I have a switch here, which is the up A, ALU up A, which means operand A, to say the value in input here is gonna set one of the two registers. So if this guy is on, the value I'm gonna input here will be for the operand A. For example, let's say I just enable the 4 last one. Then I will have the register for the operand A. We have the operand A at 1. So the 4 register for the operand A, the last ones, are gonna be 1. So here we can see the lines easily. Let's put another value. Maybe it will be more significant. Let's say we have 0, but we just put these two guys here, for example. So the lines on the left are the operand A. So we have 1, 1, and all the rest, all the lines on the left are to 0. So this is the operand A. Now that we set this, because it is set into a register, it's going to be stored in memory even if I toggle this guy. So now I'm not in operand A, so it means I'm in operand B. So the value I have in input here is now set to operand B. So I can turn it off. And let's say I'm going to put a complete different value like this one. And then we can see on the second lines that we no longer have the value before, but we have the one we just input. We just have it input here. And the first value remained because it's stored in its own register. So we have the first two here for A, and the first in the last two here for the register B. So this is just a technique to load these two things. It's made in 2 steps. So the instruction to make like A plus B is actually setting the value of A, then switching here and then inputting the value of B. So the computation is made and the value is directly returned in output here. So depending on the operand here you have the value. We have a selection here, which is the opcode, with just a selection of what kind of operand it is. And just to be accurate, I dedicated this bit for comparison mode. So like it's actually on 7 bits. And this bit just says, okay, I'm gonna select between a comparator, a comparison like greater than, equal, or something like this, or a classic operand like addition and multiplication or stuff like that. I just forgot to mention something about comparisons. Comparisons, unlike operations, only output a value on 1 bit here that is injected in the result. Is it equal, is it greater, or that kind of result. So only the lowest significant bit is going to be used as a result. And this is also mentioned in the documentation I made on the language. So that's it for the ALU. Just one thing that doesn't really appear on this design is that actually on the final design, when I exported it, I made a few modifications. The result is not directly output like here. I made a last register that I called R for result. And that register is storing the value of ALU out. The only reason I added that register is to allow the user to access the last computation that had been made at all times. It is really useful, especially when having comparisons, because you don't want to store it into memory and do something with it afterwards. You just use directly the register and then you continue your program without having to store anything and to get back the value. Alright, so here are a few operators I have in my ALU. So a basic adder, this is an overflow also. Here also you have the same kind with also an overflow at the end, but this is simplification. We just consider having the second argument as being a fixed value 1, so it makes some simplification, and so it's just a increase. You can have the same with a decrease if you set value -1 and signed with using only 1 values, for example. And the main part here, which is the biggest one, the multiplication, it is an unsigned multiplication. Let's say quickly how this multiplication works. It is based on decomposition, so actually the principle remains on individual digit multiplication. When we have a number, a big number, let's say ABC times DEF, we can decompose this by saying, okay, I'm going to take one digit at a time and multiply by another. Let's say A times DEF plus B times DEF plus C times DEF. But then we can decompose this DEF also with a times D plus A times E plus A times F, etc. And the only thing that will remain with our units here is to say we need to uprank these numbers. So because A is 100, we need to make 100 times this. And D is also 100, so let's make also this. So actually the result is an uprank. Let's say here we have 100 times 100, which makes 10,000. And this uprank multiplies a individual bit multiplication. Now, how do we make individual multiplications between 2 bits? Well, it is pretty simple in binary because our values can only be 0 or 1. So if we have anything times 0, it makes 0. The only different case is when we have 1 times 1, which means we have a result of 1. So the result is nothing more than an AND gate. What we do here in that kind of design, in that kind of square design, is to have a value on 4 bits times another value on 4 bits, and we process AND gates on each combination of bits. Each combination is going to make its own individual multiplication, so an individual AND gate. The second step is to have these upranks here that are represented by sponges. These are the first 2 individual digits of our numbers, so this is a unit times a unit. We don't have any elevation to make. Here we have a tenth and this also, so we have to elevate them and consider them a higher level, and this we have 1 more, etc. All these lamps you can see here are overflows, means we have a value that should be on 5 digits or 6 or 7. We can't represent this. I have an 8-bit computer. I want to output a value on 8-bit. If it is too much, it is an overflow. So basically you see that this makes a triangle. And so there is a lot of overflow possibilities in each of these individual values. Now, the last step, which is not the simplest one, but required to have a correct and accurate value, is to combine all these individual values together. So it can be pretty simple for values of the same rank, like these ones, for example. Just make an addition between these 2 bits and you have the value on that rank. Then you can combine together all the other ranks the same way. Pretty simple, isn't it? Well, it would be simple if we just had to take the lowest digits here and then the second one here, the third one, and the fourth. But actually these additions can result in having a carry, for example here, that makes 1 additional digit to consider in that layer. So these additions also have to be combined all together, starting from the first very bit here that can be considered in this addition, etc., etc., in the result. So actually we have a lot of additions to make, and this is why the computation we have here is quite huge. We have basically lots of adders. These are adders. We have adders here. We have adders on top here. We have adders on the other side. And all the values of the individual multiplications we have here are added together with a strategic ordering, I would say. And we have also adders here at the end. So the result here that is being output is the result of additions and other additions. A last thing that is not really practical about multiplications is the square design like this, because we need to have a value on the side and one on the other, which is not really the kind of design I have for my ALU, and also not the same one used for the adders, etc. So I made another design like this so that we can have both values on the same side, and it is a bit more compact in a certain way. And here on the top you can see the values that are really used, and all the other values are just overflows. It is essential to consider overflows in multiplications, especially. Actually, your value is not accurate if you are not considering them, because you will have a value that is incomplete. You have overflows everywhere in each of these adders, but these overflows are just considered carries for the upper levels. So these are not real actual overflows. We get overflows with all of these values, and also if that final addition here, any addition of that level returns an overflow, then we have also an overflow that can be considered here. So here we have lots of lines for the overflow that goes all the way for the last additions, the additions of last level here, and also all these values here of individual multiplications. So yeah, let's finish this video on this. We covered the most complicated part, I would say. And these are just left shift and right shift, which is not really complicated. You just take the value and put it somewhere else. So it is pretty straightforward. I hope you enjoyed that video. By the way, this is the overflow. I don't know if I mentioned it. This is the overflow general that you have from the ALU. So I hope you enjoyed, and see you again. That was IA. Let's code.